Now you can do it. I'd like to introduce Steve, KA2YHY.
Thank you. Thank you.
Take it away.
Hi, everyone. Steve, KA2YHY, and I want to go over the 3 articles that appeared over the past 6 months that I wrote for the log. The first one is this wonderful little oscilloscope that you can see, and I have it up here as well. $22 on Amazon for a decent little oscilloscope to play around with. It's certainly not a lab grade instrument, but if you've never used one before, it's quite good. Pat told me that he used it to go troubleshoot the repeater once, and works off a 9-volt battery. In this first photo that you could see here, this is right out of the box. And what I have it connected to is the built-in calibration signal. Now, for those of you who don't know what an oscilloscope does, it's more or less a voltmeter that reads continuously as time goes by. Voltage is read on the vertical or y-axis, and time goes across on the x-axis. So you could read voltage with respect to time, not just a number, but where it is as time goes by. And right now, it has this wonderful little built-in calibration signal of a square wave with a known frequency. And I'm going to use the mouse to show you that in addition to the trace of the square wave, it also has various readouts that you can select to turn on or off that will give you for instance, the peak voltage, the frequency, the RMS voltage, and so forth. For $22, it's only a single channel, but for a little more, you can get a dual channel one. They do make them. But this was, as I call it, the Skinflint Ham's oscilloscope for $22. So as I go through the article, I pointed out all the different features of it. And I do have one here for the folks that are at the meeting. They can come up and see it and touch it and so forth. So the probe is connected to this little piece of wire that I soldered onto the board. And the oscilloscope has all the basic controls that most oscilloscopes would have. The input control, grounded, AC or DC, the sensitivity of 1 volt per division of a volt, 10 millivolts, and then of course the multiplication factors of times 5, 2, and 1. On the other side of the board, I can't read them, but you have the additional controls, normal controls that old-time oscilloscopes would have, the turning knob, but this has menu buttons right here for them to go through the various controls. And as you could see, if you adjust time-based oscilloscope, oh, my internet connection is unstable. That's good. Well, anyway, in this photograph here, I have the input control set to AC, which means that the signal will be displayed both above the ground line and below the ground line in the middle of the screen. And one of the other beautiful things about this $22 oscilloscope is that it's also a memory scope. You can capture a particular waveform and freeze it and then look at it all you want later, even though it might not even exist anymore. It will put it in the memory and you could save it and look at it for later viewing. Now, this particular talk on this one is really not going to be a tutorial on oscilloscopes, but I wanted to show you the oscilloscope in real life, which I have here. And if we could somehow put that up on the screen, that would be wonderful. We have a projector here. and I have it running full time here as well. Anyway, this little blue stand I made on a 3D printer to sit it on, actually that was a stand made to hold an iPad, but it served well for the oscilloscope as well. So what to do with this oscilloscope? In the article, I gave a couple of examples of using it to troubleshoot a very simple DC power supply that got created from a step-down transformer, a little wall wart transformer, and then into a 4-diode bridge and a simple capacitor filter. And the series of photos that were in the article, as you could see now, show you the sine wave output, the step-down voltage from the step-down transformer. And then below here, you could see the actual schematic of the rectifier, the bridge rectifier, 4 diodes. Then you have a filter capacitor and a small resistor serving as a load. So I built the circuit to show you that you can use the oscilloscope to troubleshoot for instance, a very simple DC power supply. In this screenshot here on the bottom of the page, you could see the full wave rectified DC come out of the bridge, but that's certainly not flat DC that we'd like to substitute for a battery. So when we add the filter capacitor, which is right here where the mouse cursor is, you can see that we have somewhat of DC, but it has a little ripple on it because there's a load present as well, but usually doesn't bother too many things. And if you expand the sensitivity, you could really get a good look at that little bit of ripple that's riding on top of the DC. And troubleshooting, what happens if one of the diodes opens up? Well, guess what? You don't get full wave AC, and you get a pattern like in this particular screenshot. And the same thing here at the bottom. And of course, there's the ripple voltage again. But it's huge now because what I did is I added the load. And of course, now the capacitor doesn't have enough energy to keep that load well supplied. So you could use it for simple things like that. The last page of the article shows a photo of the optional case you could buy. I think the case was half the price of the oscilloscope, but it's kind of nice, but you really don't need it. And then in the Limark log article, I have all the links here for where to find the scope, where to get the case, and so forth. So if we can we switch to this?
Thanks. All right. So now they should be able to see that.
Yes,
Okay.
beautiful.
This is the same scope that was in the article and the optional case that you can get for it, which is clear acrylic case, laser cut, and does the job for a few dollars more. So before I go on to the VNA, anyone have any questions on this oscilloscope? It can show up to about 20 kilohertz. It's not very fast, but for $22, not bad. They do have others that go higher, but not very much higher. Maybe the storage is only for one screenshot. Yeah, it'll save one screenshot. Built-in memory. Yes, sir.
And display be used for something else, like the output of a Raspberry Pi or a lamp?
Depends what you want to look at. If you want to look at a data stream, you surely can.
I mean, just using the target screen. Are there any inputs to the screen? You could just use it.
Not on this model, but for more money, you can get other ones that have outputs as well. Yeah. Remember, this is the $22 skin flint ham oscilloscope. All right, so what we'll do next then will be the VNA. And I think rather than, we'll switch to the article in a minute. So this is the Nano VNA vector network analyzer, which can do an awful lot of stuff. But probably one of the things that most hams want to use it for is to check the SWR of an antenna, and it could be just about any antenna. This one is a little dual band HT antenna that I connected to it. And you could see that we have a low SWR here around 140 megahertz, and another drop off here just under 500. So this is, a typical dual band HT antenna, and you could see visually the SWR. You can also connect this up to an HF antenna. So now I have to ask if we could switch back to a new file.
Yeah.
Okay, everyone's seeing that?
Yes.
Good. Good. So this is a reprint of the article on the VNA that was in the log. And it's going to walk you through the various screens. This is essentially the same startup screen that you see when you first turn it on. It's not scrolling? So we got the menu screen here and a couple of points where you have low SWR, and you can see them. Frequencies across the bottom, SWR on the vertical scale. Now, one of the things I wanted to show, it's in the article here, is you have markers. See this little yellow triangle here? That's showing you that there is a low SWR at that particular marker, which is number 1. And it tells you what the frequency is right here, 450 megahertz. Because the marker is right here, and you could move this marker around with the stylus. Because this is a touch screen, you could move this marker anywhere you want. I think I move it over here in the next photo. Let's see. We're just expanding it there. Yeah. This one's a little blurry, but I moved the marker over to here. And then it displays the SWR at that point at 144 megahertz. And it's a little blurry, but right here it says 1 to 0.06. Yeah, very low SWR here. So once again, you're characterizing this little dual band HT rubber duck. All of the inputs you could do by direct entry on the touch screen that you can see here. You can enter in the frequency range that you want to display. You can enter the scale, the vertical scale, and so forth by direct entry. And you could narrow it as well. And if you look at this one here, this is just looking at the 2-meter band, which is a small section of what you saw before. And you get a much more accurate picture of it when you do this. And you can see right here is the sweet spot in the 2-meter band. And I can't read that frequency from here, but it looks like, no, can't read it, but it's in the 144 megahertz neighborhood. So now I want to go back to this.
No, look at the one moving that one. That one doesn't show it anyway. That's not the one. That's the other. The other one. He's got that.
As long as they can see it at home.
Yeah.
Yeah.
It makes it.
This is the SWR, but now I'm going to talk about the calibration. So, okay. So again, not to be a full tutorial on vector network analyzers, on a simpler level, you have two ways to use them. One is a single port, which is what you have here, and it's looking at just the antenna, but you could also use it as a 2-port device where you have an in and an out. And that comes by using a lot more powerful features other than just a simple SWR meter. And one of the things you could do is get this optional calibration board, okay, which has a number of different circuits on it. And you could utilize what they call the Smith chart function, or a simple network analyzer where you can see what filters look like, especially when you have a 2-port. For instance, this one here in the upper right on the circuit board is a very small surface mount low-pass filter, and it's tuned for 30 megahertz. And you really can't see it unless I zoom in a little more, but there are surface mount components here between these two micro coax connectors. One goes to the input, one goes to the output, as you can see here and here. And the circuit is in between. And if you were to connect the VNA to this particular calibration, you would see a low pass filter at about 30 megahertz where it drops off and so forth. And the next circuit is a high pass filter at 100 megahertz. Then we have a band pass here, tuned for 433 megahertz. And then they have what I call the notch filter at 6.5 megahertz. Then they have a wonderful Smith chart function that you could also use. One of the things that Dick used to talk about quite a bit on the TechNet was Smith charts, which are actually paper charts, just like a piece of graph paper, that you could use to solve complex impedance problems for tuned circuits. And again, this is not a talk about how to use a Smith chart, but if you're familiar with it at all, this is what you would see on the screen, which is the same thing as you would have on the Smith chart piece of paper that used to be used quite extensively. And for instance, now let's go back here. They give you a lot of setup circuits that you could analyze using the Smith chart. And these are, well, for instance, here you have a very simple 33 ohm circuit. It's not a complex impedance. Here's a 75 ohm. But then when you get into these other ones here in the second row, you could see, now we're going to get into circuits that have impedances that can be shown on the Smith chart. For instance, here you have a capacitor and a resistor. Number 10, you have a capacitor and an inductor. And the shape that the plot takes on the Smith chart, this characteristic shape is always an RL circuit. Now here you have what sometimes is called a tank circuit, where you have a capacitor, resistor, and inductor, and you could see this little spiral, which is what you would get on the Smith chart if you plotted all those points manually, or you use the little vector network analyzer, and you can determine right away what the impedance of this particular network is. And then they have 3 different other loads or circuits that they give you to self-calibrate the VNA, essentially a short, an open, or I believe a 50 or 75 ohm load. To make, if you want to make accurate measurements, you need to calibrate it first, and then it will be accurate after that. But this little gadget is an optional thing, doesn't come with it. I found it on Amazon for about 20 bucks, and it's made specifically to go with the Vector VNA. Now this blue thing here is the case, which I printed. That doesn't come with it, but there are plenty of cases that you could download for free. And if you have a 3D printer, you could print them out. Any questions on the VNA? We'll go over to the last project, which was the Bluetooth MP3 player. And we could do, I don't know if I could focus on this. Let's see.
Flip it around, it's upside down.
Okay. So this is a 3D printed plastic case that I made for this part, which is a Bluetooth MP3 player. And it runs off 12 volts or 9 volts, anything. Right now it's automatically switching into the Bluetooth mode, but you could see that it has a USB port. It has a micro SD card, and you used to be able to buy these modules for about, oh, let me just stop that a minute. Pause it. Well, you could listen to the music if you like, but this is playing off the MP3 files that I have on this card. You could also set this up by controlling the mode. You have FM broadcast receiver. It has an auxiliary input. Or in Bluetooth mode, you could play any music you might have on a smartphone or any device that can connect to this Bluetooth as well. And this was described in the article as well. But I'm going to turn up the volume, and for a little gadget like this, it has pretty good sound. So I think we'll bypass the article, but we'll take any questions anyone might have.
Question. If you're going to use this for ham radio, and you connect the audio, it's obvious the audio works.
Yeah.
Right? What do you do about the push talk function? How does that work through Bluetooth along with the audio?
There are, forget about this project, but in general, that question, you want to have a Bluetooth connection to your radio in your car. There are many companies now that will sell a Bluetooth push-to-talk remote switch. It has a little battery in it. So you press that switch and it Bluetooths to the radio. I know Connect System has one. I'm sure Yaesu and Campolo. Anytone has it too. Yeah. You need the remote push-to-talk. There's no other way. So anyway, that's the 3 projects that were published in the log. If anyone wants to come up and look at it. The last thing I want to show you, let's go back to this one more time. This
Which
projector.
okay, sorry.
If you really want to learn how to use this nano DNA, this book is available on Amazon. Unfortunately, not in print. It only comes through as an ebook, which I purchased. I think it was $10, and I printed it out myself. And if anyone has one of these nano VNAs, you can very easily get lost in the menus. It has so much functionality. The big job is to remember where those functions are in the menus. So probably the best thing that comes out of the book is this function chart that lists every function. And this is what ham radios need. When you buy a ham radio, that you have to hold the menu button down for 2 seconds, get into the secondary menu, then switch to the third menu. This is what every ham radio should have too, a function chart. And this will, every one of these rectangle boxes with something in it is one of the functions. And if you follow the lines from the main menu, it'll tell you how to get to every function. So this is worth the weight of the whole book by itself. But if you want to learn how to use the nano VNA, this is what the contents has. It's really good. I went through it, and the book really helped me to learn how to use the calibration board, which I didn't really know much until I read the book. But it's quite good. Any questions? I'll leave this stuff up here if anyone wants to look at it. And that's it. So